Anyway, I'm going to talk to you today about some work that we've done at BRACE. A lot of people are working on why low unit cell size USY sieves make high octane gasoline, what selectivities that involves and how that comes about. I'm going to talk to you about some of the work that we've done with that. Structure and selectivity to low unit cell phlogisite. It's Wu Chang, Mike Shatlock, and the NMR company. This is sort of a background slide. Denise Bartholomew and others have shown that there's weak and strong sites in USY type materials. And Dempsey, especially Dempsey, suggested that acid strength is related to site isolation, which has been something that people have been working on now for about 10 or 20 years. Pine and others showed that basically octane selectivity is related to a high silica-aluminum ratio in the phlogisite is related to relatively low numbers of aluminums per unit cell. And Fock selectivity has a similar relationship to unit cell, although it's not the same relationship. One of the problems is people know pretty much about the structure of phlogisite, but they don't know exactly where the aluminums are. They know what the structure, they know the oxygens, they know where the hydrogens are more or less. They know where the silicons are, but the XRD and other techniques have not really shown where the aluminums are. Lipna and some others were able to use magic axial spinning NMR to identify silicas in different with different coordinations of aluminum. And this provides an indirect probe for the kind of aluminum siting that you have. For example, to what degree you have a silicon with, say, 2 aluminums next to each. If you have a silicon attached to 2 aluminums, you get 1 shift. 0 aluminums, you get a different shift. 2 aluminums, for example, in that top slide. And it's 4 means that you have a silicon attached to 4 different aluminums through an oxygen bridge. So this gives you some way of probing what kind of aluminum distributions you have in the zeolite. The top one is the phlogisite X with a relatively low silicon-aluminum ratio. You notice there that there are still some silicons that don't have any aluminum directly connected to them. The one on the bottom is a more normal, typical phlogisite. Phlogisite consists of hexagonal prisms. They're connected together. The hexagonal prisms can contain 6, 5, 4, 3, 2, 1, or 0 aluminum atoms. There is a statistical mechanical procedure that you can go through and you can calculate in any assembly of these prisms what's the most probable distribution of those prisms. And you do it the same way using Lagrange multipliers and that same business. In any event, if you do that, you can pretty much calculate what a aluminum distribution in a phlogisite would look like if there were no energetic, no avoidance rules, no energetic constraints or anything else. Wrong way. If you do that, what you do is you get that solid curve. This is the curve for a silicon attached to 4 aluminums. As the number of silicons per unit cell, there's 192 total atoms in a unit cell. As the number of silicons increases, the number of silicons attached to 4 aluminums decreases. And in fact, it decreases faster. The data points are experimental data points, which are taken from the literature. About a third of them were determined in our laboratory. It turns out that the silicons attached to 4 aluminums, that kind of silicon decreases in population faster